So I want to give you an example with some actual numbers. Now, I make fun of the XKCD joke about returning 4 for the random numbers, but when you actually go to test one of these systems, that's exactly what you want to do. And in Go, the way I do it is I set up an interface in the actual code that uses either the real thing by default, the real random number generator, or then only in the test code, I overwrite the interface with a pointer to something that returns basically either a constant or a series of constants, so that I can get my test to repeat over and over. Now, for something like this, what you do for testing is you set up a teeny test. In this case, my modulo is 31, and you work out some values like this. So for the double, you're talking about 2 times a particular point where you want to test it, and my point is right there. Okay, that's 314. And when I test with this point, I calculate the slope. I go zooming off down here, which, oops, went the wrong way. I go zooming off up here, which wraps around to down there, and again, and again. And I come around and I get to this next point, okay, which I'm trying to do my calculation against, okay. And when I calculate it, and then I go find the corresponding point on the other side of the axis, or the other side of the curve, which is up here, which gives me my 1922. And the way that I got the 11 is 2 times 21 mod 31 is 11. So with just a little bit of calculation and an example, then you can actually go and test this thing without numbers that are like completely outlandishly large. And when you get it to work for the little numbers, the magic of computers is then you go and test the big numbers and you find out that, yeah, it should work for the big numbers, barring some weird sort of conversion error. So we've got some particular curve like P25519 or P256 with an agreed upon G value. That's our generator. And both the sender and the receiver know this. We generate a private key, which is some point on the curve. And we get to the public key by multiplying the generator times the private key. And that's your addition double stuff to get to your public key. And that's the relationship between the public and the private key. Now, we can use this for signing, okay, by just generating another point and doing some calculations between the two. And at a certain level, you've been through this in a homework, but this is down at the grunge level of how does this actually work. So your public key and your private key, okay, if you're going to sign a document, okay, you have some document, you take the hash of it. Again, the way that I go about testing this is I return like nice constant values for my hashes in tests, like 14. And I'm going to do this again with my modulo 31 space, which is nice and tiny. I can go with my calculator and calculate things out on this space and get results that I can then check. So the generator, okay, in this particular case, I've picked the generator as 0, 2, which is this little tiny value over here. We've got a private key of 17.9, and we pick another random point out there. And the signature, okay, is then the hash plus the x value 13 times this value 7, okay, which is right there for the generators 7 times. And we divide it, we do mod 31, we end up with a signature point. So signatures are a point out here in the plane. And then when we go back to calculate it the other way, I've worked out a set of numbers that walks through that allows you to calculate going the other way and how it actually verifies it. And it gets back to, at the end, yes, something that we can match and we can verify. But here's a set of values that's all calculated out, that's all like single small digits that you can walk through and use for testing. And you can like make sense out of the testing of one of these things and actually check the values without it being huge values. And you may not want to use my values, but all you got to do is sit down and build a set of values that's in some prime numbers modulo range. Use the same curves that you would normally use, But instead of having a huge range like they do in the real world, you do a little tiny set with little tiny numbers. You walk through all the numbers and do all the calculations, and you can work out the details. And you've got to fix your random numbers so that instead of it being random, it's like an XKCD, return the constant 4 for your random number. And suddenly these things become testable. Now for the real numbers, if you look at the E25519, here's your actual numbers that you've got for your formula, okay? Which, that's big enough, and then the prime number is the prime of 2 to the 255 minus 19. That's why it gets its name from. And, you know, these things are, these are the little small constants in it. Like that number right there is one of the small constants. So testing with the real things is all, you know, big complicated numbers that you just can't quite digest, and you can't test with them in any reasonable fashion. So that's why the effort to get a set of values like that is a similar curve, that you can work out all the numbers, that you can actually look at the numbers and test them on a calculator and be able to build them. Once you've got that, it isn't so hard to test. Okay. I do prefer the 25519. Okay. And here's the quote. Okay. I no longer trust the constants. I believe the NSA has manipulated them through their relationship with industry. And Bruce Shear, okay, is a cryptographer who won the NIST competition and developed the other encryption standard that is used out there. And he's the guy that came up with this 25519 encryption, so you're not using NSA's P256. And we don't know for certain that P256 has problems, but there's some unusual things going on around the P256. And pretty much that's why everybody in the world is using Bruce Shear's other curve, 25519. So you should be aware of that. Other than that, you know, there's good reason to believe that these curves actually work and this encryption works. Now, in a real-world scenario of how these things come together, generally speaking, beyond the land of signatures or key exchange, we don't actually use the public key encryption. What we do is you'll set up some system, you'll use a signature, or you'll use a key exchange, and at the end of using the key exchange, what you have is both the sender and the receiver have agreed upon keys that are 256-bit numbers. And then you do all the communication using a non-public key encryption system. So this is only the front end of the encryption, usually, not the entire encryption. The problem is that the amount of data that you can actually encrypt with one of these systems is usually very limited. It's a 256-bit value. That's all you can encrypt with it. And then you've got to do some stuff to encrypt the next 256-bit value. So 32 bytes at a time is all you can encrypt. But with key exchange, you encrypt that value, and then you immediately move on to the next thing, which is an encryption system that is more suited for how you're communicating. And both the calculations for this and these other encryption schemes, like Cha-Cha or one of those, are available on most hardware like Intel 86 and AMD ARM hardware, built into the instruction set of the hardware. So it's really, really fast once you get past your setup phase.